I'd like to welcome everybody to this week's Western Hemisphere Colloquium on Geometry and Physics. I'll just go over our usual procedures before we get started. The participants are muted during the lecture. If you have questions for the speaker, please send them by chat to everybody. And you're welcome or encouraged to answer the questions during the chat, especially if you're one of David's collaborators. All remaining questions I will aggregate and take them on to the speaker. After the talk, we'll have a Q&A. Please use Zoom's raise hand features, and I will call on you and ask you to unmute yourself so you can ask those questions. The talk is 1 hour, scheduled for 1 hour with 15 minutes Q&A. We're not super strict here with the stopwatch, but that's the guidelines. And now it's my pleasure to welcome today's speaker, David Jordan. His title is Quantum Geometric Langlands as a Fully Extended TFT.
Okay, great. Thank you very much for the chance to speak here. One more point of order. I love it when people make their video visible. If you're the kind of person who likes to smile and nod along during talks, feel free to turn your video on. Hi, Aaron. Okay, so right, I want to talk today about quantum geometric Langlands as a fully extended TFT. So I'll be focusing on the topological field theory properties. And so I'll touch on various joint works with all the lovely people pictured here. So I'll start with some introduction reminders about character varieties, character stacks, and their quantizations. And the focus of the talk will be some recent approaches using factorization homology and cobordism hypothesis. And then at the end of the talk, I want to finish with some applications of these ideas to quantum topology and representation theory. Before I launch into it, though, the sort of broader goals that I hope people take away from the talk is I want to try and emphasize the importance of using stacks and higher categories and how they make your life much easier when constructing these field theories. I certainly want to introduce the notion of factorization homology, and especially stratified factorization homology, which was recently introduced by Ayala, Francis, and Tanaka. This is just a beautiful theory. And it gives rise to a zoo of interesting defects that we'll study. So more closely tied to the physics, I want to emphasize the sort of four-dimensional Kapustin-Witten viewpoint on skein theory, as opposed to traditionally people have looked at it from a 3D Chern-Simons point of view. And then sort of building on that at the end, I want to share a recent conjecture of myself and my collaborators, which is a sort of instance of S-duality or Langlands duality as it appears in the skein theory of three manifolds. Okay, so let's get started. Right, so the basic geometric object that we want to study is what's called a G-local system. So this is, so we have some space, typically a manifold X, and we fix a reductive group G. And a G-local system is just a principal G bundle over X. So maybe here's X, and then the fibers of this thing are all G, non-canonically identified with G. And then we have one more bit of data, which is a flat connection. So the different fibers, we have a way of identifying fibers and lifting paths. And so the primary object of study that we want to consider is the moduli space of these things. So it's just denoted like this, character stack of X. So I'll suppress the dependence on G. So this is moduli space of G local systems on X up to isomorphism. And it's not too hard to convince yourself that this is the same as studying simply homomorphisms from pi 1 of X into G at some base point up to the conjugation action by G. Okay. And the reason I say character stack here is that when we quotient by isomorphisms, there really are automorphisms on some points. And so it's going to be important to treat this as a stack. But the nice thing is that it's a very easy type of stack, which is a quotient stack. It's a quotient of an affine variety by an algebraic group. So we can consider instead, it's called the framed character variety. So this is pairs of a G local system on X and a trivialization of E over the base point, and we want to identify that explicitly with X. And then we consider those up to the natural notion of isomorphism. And when we translate that over to pi 1, then this is maps from pi 1 of X to G, full stop. So there's no more automorphisms anymore. Okay, and so for instance, from the second description, we see that this character stack is just the quotient of the framed character variety by the group G. And this is a nice affine variety. For instance, if we just choose a presentation of pi 1 of X, finite presentation with finitely many generators and finitely many relations, well, we just get a presentation of it as an affine algebraic variety. Okay, so this is, as a stack, it's an extremely nice stack. So first of all, it has a shifted symplectic structure that was developed by Pantev, Tohen, Vecchia, and Vazossi. And when the dimension of X is 2, i.e. when X is just a topological surface, then this recovers what goes by many names, either the Atiyah-Bott or Goldman or Fock-Rossley-Poisson bracket. And when the dimension of X is 3, so we're talking about 3 manifolds, we can think of this as the coming from the BV structure on the critical locus of the Chern-Simons action functional. Okay. So, but this exists in every dimension, and it's a very interesting structure to study. So this is a physics colloquium, so I should mention that character stacks and their quantizations definitely play an important role in some physical theories. Now, I should say I'm not a physicist, so this is my olive branch, if you will. So apologies if I make any errors. So the Kapustin-Witten twist of 4D n equals 4 theory. So in this very important paper, they identified that geometric Langlands, the right way to study it as a field theory is using this particular twist of n equals 4 theory. And so this comes with a dependence on the parameter psi in their work. So psi is just a complex parameter. And they tell us that on surfaces, what we should be attaching is roughly the Fukaya category of the cotangent bundle of bund G. So this is sometimes called the Hitchin moduli space. Okay. But unfortunately, that's mathematically ill-defined because this is a proper stack, and so it's also non-compact. So the Fukaya category simply isn't well defined. So mathematically, there's sort of two avatars of this. So there's what's called the de Rham model due to Beilinson and Drinfeld, essentially, and many others. And then there's the Betti model proposed by Ben-Zvi and Nadler. And so in the de Rham model, you're studying D modules on bund G of your algebraic curve. And in the Betti model, you're studying rather quasi-coherent sheaves on local systems, so on the character stack, in fact. Okay. And so these are actually both when the parameter psi is at infinity. But we can vary psi, and when we vary psi, that's where the quantum parameter enters in. So here we can consider, well, they're just called psi twisted D modules on bund G. And these feature in the quantum geometric Langlands correspondence. And on the Betti side, well, we're studying some kind of deformation quantization of the character stack. Okay, and it's deformation quantizations of the character stack, certain canonical ones that are going to be the focus of today's talk. Okay. Another place that this appears, which is really the same place in disguise, but let me mention it. If we look at 4D n equals 2 theories, certain ones called theories of class S that are determined from a Riemann surface. So that's a 4D theory. We can compactify it on a circle, and we get certain 3D n equals 4 theories that have the nickname Sicilian theories. I think due to, I'm not sure who gave this name. So if we look at the Coulomb branch of this theory, that is, if we study its value on the 2-sphere, then we again get the Hitchin system. And I believe this is due to Gayotto, Moore, and Knightsky. And again, a certain hyperkähler rotation of the Hitchin system is again this character stack of the surface. Okay, so the same character stack arises as a Coulomb branch. And if we do what's called turning on the omega background, so introducing a rotation parameter on this 2-sphere, then that should roughly correspond to the Q deformation. Okay. So with these motivations in hand, we want to try to understand what sort of topological field theory properties can we expect from character stacks, and especially from their quantizations. Okay. Now I keep saying character stack, and I think the phrase character variety is probably much more familiar to people. So I just want to demystify that a bit and say that the way that we study a quotient stack is by looking at the category of sheaves. So what this means is that the algebra of functions O of x on our affine variety, it has an action of the group G, a representation of the group G. And so when we study the stack x mod G, we just, if you like, it's almost a definition that quasi-coherent sheaves on the stack, you consider O of x modules which are G equivariant. So it's a module for the algebra of functions on X. It's also a module for the group, and there's a compatibility there. And we study that. It's an abelian category, and that is the category of quasi-coherent sheaves on the stack. So when people talk about character varieties, what they're usually doing is instead you take that same algebra of functions, you look at the subalgebra of G invariants, and you just study its modules directly. Okay. And the key thing I want to emphasize is that there's a functor from the category associated to the stack to the category associated to the variety, but the key thing is it's destructive. So it loses information, and what it loses in this case is the glue that you need in order to have a TFT. So I thought before moving on, it would be interesting to do a sort of baby example where you see this. So the motto is that character stacks glue and their quotient varieties don't. So for this example, we're going to consider the character stack of the circle, S1. And hence we're going to study the category, which I'm going to start calling Z of S1, which is quasi-coherent sheaves on the character stack. Okay, and so before we even start the example, I've written the answer down here. So the framed character variety of S1 is just G. That's because, well, pi1 of S1 is just the integer Z, and so we just have to say where do we send a generator. The character stack of S1 is the quotient of G by its own conjugation action, and that's because we need to forget the choice of basis that we've chosen there. And the character variety of S1 is then G invariant functions, which we can identify as a spectrum of G invariant functions. So that's the Cartan mod W. Okay, so those are three all interesting spaces. And let's see how we compute those spaces using character stacks. Okay, so the sort of zeroth computation you need to do is that, okay, quasi-coherent sheaves on the stack, which is a single point quotiented by the trivial group action. So going back to our definition above, that's just G equivariant vector spaces. And that's almost by definition just the category of representations of the group G. Okay, so we're going to use that computation. So if we compute the framed character variety of the interval 0, 1, so the framed character variety is just a point. pi1 is trivial, so there's just one point and it has no automorphisms because we framed it. The character stack of the interval is point mod g by the above. And then again, if we take the character variety of the interval, it's again a point. Okay, so with those computations, let's look at z of S1. And let's be optimistic that we have a topological field theory. So if we have a topological field theory that says that I can compute this as z of this, so I'll explain the formula in a second. So we compute the category attached to the interval. We tensor it with the category attached to the complementary interval, and we take the tensor product over the category attached to the disjoint union of two intervals. So what we're doing here is we're imagining a composition of cobordisms like so for the circle. Okay. So this tells us that we need to compute the category rep G, tensor the category rep G over the category rep G tensor squared. And well, I won't do the computation, but it is really a few lines computation. This is identical to O of G modules, so G equivariant O of G modules, and that is exactly Z of the circle. Okay. So right, so what that illustrates is that if you work with the stacks, then you have the glue. Of course, if we had tried to do this with the framed character variety or with the character variety itself, we could never hope to get something as interesting as H mod W just by gluing copies of vector spaces together. It's simply not possible. Okay. Maybe I should pause if, Sheldon, if there's any questions you'd like to relay?
No, all questions have been answered in the chat.
Okay, great. Okay, so right, so the interest here is in quantizing the character variety, and let me especially focus on quantization of, in the case of surfaces. So historically, the focus, as I said, has been on character varieties rather than character stacks, and so let me recall what's been done. So Brzezinski and Turayev, like in 88, 89, so very early on, considered the case of G equals SL2, and they defined what's called the skein module of a three manifold. And so this is just the vector space spanned by links. So M needs to be an oriented three manifold, modulo the skein relations. So probably these are familiar to many of you. So we have that this guy is equal to q to the 1/2 times this, plus q to the -1/2 times this. And of course, what this diagram means is if I ever encounter anywhere in the three manifold inside some little ball, if I ever encounter an overcrossing like that sitting inside some little sphere, then I can replace it with this linear combination. So that's the definition that makes sense for any three manifold, and it gives you a vector space. And if we consider a surface, well, we make it into a three manifold by just crossing it with the interval, and this is now an algebra. It's called the skein algebra of the surface via just stacking in the interval direction. Okay. And so when you set q equals 1, actually both Brzezinski and Turayev had shown that when you just plug q equals 1, you recover, first of all, commutative algebra, because the difference between an over and an undercrossing disappears. You get a commutative algebra, and moreover, it's precisely the algebra of functions on the SL2 character variety of S. and you think of a loop as corresponding to the trace of the monodromy of that expression. And in a paper by Bullock, Froman, and Kanya Bartosinska, they showed that actually, moreover, this is a flat deformation, so it behaves well as you sort of move away from q equals to 1, and it recovers the Atiyah-Bott-Goldman-Poisson bracket on the surface. So that's a really nice result that tells you that skein algebras quantize the character varieties. So around the same time, a few years later, Alexeyev, Grossa, and Shomerus gave a more algebraic quantization. So this works for any G, but it requires that you have a punctured surface. So I'll denote it by sigma G comma R. So genus G and R punctures. And so if you think about it for a moment, as soon as you have at least one puncture, then this is actually just, the pi 1 is just a free group. And so this is just a bunch of copies of the group G. And so then the algebra of functions on the framed character variety is just a big tensor product of copies of the coordinate algebra of the group. And so what these guys did is they said, well, let's just define an algebra. And I'll just denote it by A of sigma. And what they did is there was a well-known algebra called OQG, a standard Q deformation of the algebra of functions on the group. And you just take, oh dear, okay. My pen has stopped functioning. Really would like it to function somewhere. Okay, I thought this might happen. I've got it back up. Okay, and we're back. Okay, so sorry for the hot pink. Right, so this algebra A of S that they define attached to the surface is a copy of the same number of copies of O of G as you had before, but now with this quantum algebra. And the cross relations are a bit complicated. They depend, of course, on the genus and the rank, and they're expressed using the quantum R matrices for the quantum group. Okay, so we'll come back to these algebras in a bit. And then the third one I want to mention is a quantum cluster algebra approach by Fock and Gonchreff. So they consider what's called the decorated character variety. So you add some extra sort of partial framing data called a B reduction near the boundaries of the surface. And what they show first classically is that if you have a triangulation, if you choose a triangulation of the surface, that determines you an open set inside the character variety. And that open set is, it actually has no stabilizer, so it's actually an honest variety, it's not a stack. They don't really show this, but that's true. And then the variety there is just a torus, so it's just a copy of C star to a certain rank, which is the number of edges in the triangulation in the SL2 case. And moreover, the cross relations are encoded in a Poisson bracket, and the Poisson bracket is just what I call toric log canonical, or what they call toric log canonical. So the Poisson bracket of xij is quadratic, and it's just a certain multiple of xi times xj. And so The quantization that they propose is that you just have some non-commuting variables, capital Xi, capital Xj, and they Q commute according to the same integers. And so in a completely obvious way, that is a quantization of this chart. But moreover, what they show is that if you do change of triangulation, so if you look at a quadrilateral, there's two possible ways to triangulate it. And if you change triangulation, then there's a very rigid transformation that appears that's called a cluster mutation, and they're able to quantize that as well. Okay, so these are sort of the three classical approaches. And it's worth remarking that, all of these are like 20, 30 years old, and there's not until some of the work I'll discuss a systematic way to even see that they're the same. They're all deformation quantizations of the same thing, but comparing them directly to one another is not so straightforward. Okay. All right. So now I want to shift a bit and talk about how do you construct the quantization of this stack? How do you construct the categories that one should associate and call the quantum character stack? The first hint is in a paper of Ben-Zvi, Francis, and Nadler, where they tell us that we should think about the character stack of some manifold as a sigma model. So we should consider maps from X into the classifying space BG. And if you think about it, that is what a character stack is. It's we're giving a map into the classifying space, and from that you see that it satisfies excision. So if I have a surface which is glued out of two smaller surfaces along an interval, or more generally an N manifold glued in this way as a composition of cobordisms, well then the character stack of the big thing is just the product of the character stacks of the two components relative to the boundary. So you're saying that you just, to prescribe a map, you need to say what it does here, you need to say what it does here, and then you need to make sure that it coincides. And the beauty of the stacky language is that, this wouldn't be true at the level of character varieties. It's only true at the level of character stacks, because you have to be worried about automorphisms that might arise on that cylindrical boundary. And so as a consequence of this geometric formula, they get an algebraic formula which says that the category valued invariant that I've been calling Z of S is this tensor product in the same way that I did in that example. Okay, so you can compute algebraically the two pieces, and there's an algebraic prescription for gluing them together. Okay, so of course, a little bit before this work, Lurie and had proposed, and then Ayala and Francis had constructed a universal invariant called factorization homology, which satisfies this excision property. So factorization homology, it's a machine. You plug in two things, an N manifold called M and an EN algebra called A. It spits you out an invariant called ZA of M. And in some places you'll see it denoted like this. And this is a category for us today. It could also, the machinery is very general. You could consider factorization homology valued in vector spaces or chain complexes or infinity categories. But for us today, it's just valued in like abelian categories. So it's quite concrete. And the way that you might want to think about this in physical terms is that the EN algebra is determining you the local observables. And so it's an algebra. And then the factorization homology is the resulting algebra of global observables. Okay. Something that's special to this that makes it a topological field theory and not a general quantum field theory. So factorization algebras apply in much more general theories, but what makes this topological is as follows. So suppose I have some surface and I choose an embedding of a bunch of disks into the surface. and I color each of those disks with an object with a representation of G. Okay, then part of the machine of factorization homology is it gives me an object, which is the image of those things. It gives me an object sitting inside of this category that I've just constructed. So this is not just some abstract category, it's a category that comes with a whole bunch of objects. In fact, they generate. And what makes it topological is that if I start to move these disks around, so if I consider some isotopy of these of this embedding, then I get automorphisms of those objects. So in fact, I get actions of braid groups of the surface, and moreover, the entire category itself has an action of the mapping class group of the surface. So you get these categories that just have this really rich topological nature that they inherit from this general machine of factorization homology. Okay. My collaborator Adrian Brochet and I, we were studying some constructions that we had come across in representation theory of quantum groups that had exactly this flavor. So there was some sort of invariant that you could attach to a surface. It had these braid group actions, it had these mapping class group actions. And at the time I was a postdoc with David Ben-Zvi. And when he saw this, he said, okay, this sounds like you're doing factorization homology. And so that began a very fun collaboration to define what we call quantum character stacks. And so the key idea, the key input is that if you look at the n=2 case, so on surfaces, then an E2 algebra in categories is just the same thing as a braided tensor category. Okay. And so then what we do is we define a new invariant attached to a surface, which is instead of taking rep G, representations of the group G as a symmetric monoidal category, we take rep QG, the representation of the quantum group, regarded as a braided tensor category. And right out of the box, Ayala Francis lets you make sense of this definition. And in our first few papers, we make big use out of the fact that if I have a surface with a puncture, and if I have some interval sitting in the boundary, call that a gate, then I can start inserting disks in through this gate. And what it does is it tells me that this is not just a category, but it's a module for this commutative algebra. Rep QG I think of as a categorified commutative algebra. And so now I want to get a handle on this strange category that's defined by some formula by Ayala and Francis that I can't understand. And so what I try to do is I say, if I had a vector space, I should try to find algebras that act on it and try to use that to study the structure of the vector space. Well, here I want to do the same thing at one category level higher. Okay. And so using this technique, we were able to show that if you have a punctured surface and you choose one of these gates, then you can identify the category with the category of modules for these Alexeyev-Gross-Schomerus algebras. So these very explicitly defined algebras that they had defined many years earlier. And we also showed that if you have a closed surface, then what you can do is you can compute the answer in terms of these AGS algebras for the punctured surface by just removing some point. And then there's a process called quantum Hamiltonian reduction, which was already sort of well established, that lets you move from the punctured surface to the closed surface. Okay. And using these ideas, we were able to see the so-called spherical DAHA, so an important and interesting algebra that I won't spend much time on, that the spherical DAHA arises from considering the GLN factorization homology of the closed torus. Okay, and the idea is that you decompose the closed torus as a union of the punctured torus with the boundary, this prescribes you something called quantum Hamiltonian reduction, and we were able to just compute this in quite explicit detail. So this is, the general machinery was done in a paper with Ben-Zvi and Brochet. With my co-author, Martina Balagovic, we computed it in quite a bit of detail for GL2. And then with Gunningham and Vazirani, we have some extension of these results that gives you the Q equals T specialization for any rank. And so a third way that you can think about these factorization homologies is work of Juliette Cook. And she shows that for any surface at all, factorization homology recovers what's called the free co-completion, so a certain natural construction from the skein category of defined by Kevin Walker. And so the skein category is quite like the skein algebra, except that you have these structures that we've kind of already seen before. So objects of the skein category are you choose a bunch of points or really disks on the surface. You color those with representations, and those define objects. And then HOMs between two such things are given by sort of compatible colored tangles between so this is one object A. Sorry, this is really hard to write like this. And this is one object B. And then HOMs from A to B is all the diagrams you can write like this. So Walker had introduced this, and Juliette Cook showed that the skein categories also satisfy this excision. And then because Ayala Francis tell you that it's the universal invariant satisfying excision, that gives you this other description. Okay. So I want to mention also later work of Ayala Francis together with Tanaka. Let's just consider stratified manifolds, again, of any dimension, but my interests are in dimension 2 and 3. And so the stratified factorization homology, you can consider now manifolds with defects, but you still get all of the package of functoriality and excision that we had before. And of course, the locality is replaced by richer structures. So for instance, if we consider the stratified manifold, which is just a single point sitting inside R2. Before, when we didn't have this point, we had to give data, which was the data of a braided tensor category. And so now we have to give two pieces of data. We have to give the braided tensor category that lives out here in the generic part of the manifold. And we have to say what we do with this red dot. And it turns out that a lot of people have been studying what you do with the red dot, and it's called braided module categories. So these were already being studied before they were associated with this picture. Okay, so that's the sort of local data. And then the game is that now you can consider an arbitrary manifold that has, as long as its local picture looks either completely vanilla or just has singularities, defects like that. So for instance, a once punctured torus we could consider, but instead of a puncture, we treat that as a singularity. And so the kinds of places you can look for braided module categories, you can look at conjugacy classes, G Hamiltonian spaces, and their quantizations. So for instance, if we plug in representations of quantum GLN, and we take the so-called mirabolic conjugacy class, and we look at its quantization, this recovers now from a once once marked torus. We get the type A DAHA for completely general parameters Q not necessarily equal to T. So that again, the way I'm phrasing it for GL2 and arbitrary parameters, it was done in this paper of mine with Martina Balagovic. For Q a root of unity, it was done in different language by Varaniello Vassaro. Right, so that's the story there. You can also consider these sorts of defects. So we have two planar regions, vanilla region and I guess this is like lemon sherbet. And so there, now the border between those, so those are both braided tensor categories. The boundary between them, this pink region, needs to be what's called a central tensor category. So it's a tensor category which is acted on by the braided tensor categories. And then the line in the middle has a lot of structure. So it's a bimodule for the two lines, and it's a module for the braided tensor categories, and there's a whole zoo of compatibilities there. And it turns out what this encodes is the calculus of parabolic induction, flag varieties, and Stokes phenomena. So as one example, if I can take for my braided tensor categories representations of quantum G and quantum T. T is the Cartan. Sorry, I used H before, but we'll use T. And then it turns out that rep QB is a perfectly good interface between T and G. And then we can even go farther, and we can consider different Borels. So different Borels will differ by conjugation by a Weil group element. And so we can consider B and also B conjugated by some Weil group element. And then the sort of thing that we could put as a defect there, as a point defect, would be the intersection of those two Borels. Okay, so this is a sort of thing that you can do. And the nice thing is you just turn on the Q parameter in a well understood way, and you get these really interesting quantizations. So for instance, if we take some surface, we choose some regions in the boundary. So they can either be contractible regions on the boundary like this one, or they can be entire boundary components like this one. And then what we do is we enhance it a bit. We put a T inside, we put a little B boundary, and then we put G in the middle, and we consider this space. Well, classically, what you get is exactly what I would call the decorated character stack. So the Factorization style thing where you have a B reduction at the boundary. And that's exactly what's being encoded on these red lines, classically. And in recent work with Ian Lay, Gus Schrader, and Sasha Shapiro, which I'll talk about more on the next slide, we actually show that the sort of decorated character stacks and their quantizations that you construct in this universal way contain within them the Factorization construction, which was done in a more generators and relations kind of way. So it gives a sort of new point of view, I guess, on Factorization. And a lot of things that you have to prove by hand in cluster theory. So for instance, the fact that the mapping class group acts, that's a theorem in cluster world, and it's just a tautology in this world because it's defined using something universal. In some more work in progress with Andrea Appel and Brent Pem, we're studying, so Philip Bolch has studied a lot quantization of Stokes phenomena, and you can sort of model a higher order singularity, so non an irregular singularity. You can model it both classically and at the quantum level with these kinds of defects, and so we have some work to sort of study these quantizations, relate them to more explicit stuff done by Bolch. Let me just mention one other type of singularity that you can study is orbifold singularities. So far these were just ordinary defects, but there's not been a lot of work on factorization homology of orbifolds, but Tim Wielink has studied them in the context of what are called quantum symmetric pairs and universal K matrices. So this is another big topic in quantum algebra, quantum topology, is understanding these quantum symmetric pairs, and they really do, what Tim shows is that they are the local coefficients for a orbifold factorization homology if your group is just Z2. So again, the kind of inputs you might consider are like symmetric spaces, and the kind of outputs you get are orbifold character stacks. And just one other example that sort of motivated a lot of Tim's work. So if we consider the 2 torus again, and we consider the negation action. So here I've drawn that as rotation about some axis as it sits in 3-dimensional space. So in some earlier work with Xiaoguang Ma, I had studied some braid group actions that you construct using quantum groups sort of technology. And it was again this sort of generators and relations. Well, here's some maps. They satisfy the braid group action, and it descends to the double affine Heck algebra. And some work in progress with Tim Wielink, we can understand that those things that we were computing about the type C DAHA rather than type A DAHA, you can understand those purely from factorization homology principles, just exactly the type C analog of what we were doing up here. Okay, so that's the general picture. I guess I want to talk about this because it's sort of the thing I'm working on the most right now. So for the Factorization picture, so we're considering this decorated character stack. So that is, we have a G local system in the white region, a T local system specified in the yellow region, and then a B reduction along the red region of the resulting G cross T local system. So this is slightly different than what they define, but it's essentially the same. And so, right, so our proposal to quantize this is that you just replace the factorization homology appearing with G, with rep QG, rep QB, and rep QT. And then there's a theorem, which I hope to illustrate with some drawing, but that's going to be, well, maybe I can, no, even my touchpad is not working. So just from that surface, you define a category. What you can then do is you can choose a triangulation of the surface. And when you choose a triangulation of the surface, we show that that determines a certain subcategory. So for instance, here's a triangulation of this surface. I can go here. I can go here. So now that's one triangle, and that's another triangle. But I could have also done a more exotic triangulation. I could have done something like, let's see if I can remember what to do. So I go, yes, I can go up and around here, and then I can go up here, for instance. So there's a collection of charts that you get, one for each triangulation. And what we do is we show that as a consequence of this excision axiom that defines factorization homology, you can actually just do a computation rather than a definition, and you identify these subcategories inside there with the category of modules for a quantum torus. And the point is, it's exactly the same one. It has the exact same presentation as the Factorization prescription. And as you change triangulation, then you're moving around in these subcategories, and the way that you move is, we also show, is given in formulas by cluster mutation. I should also mention, so that last bit about the cluster mutation, we got a major hint on this from a really beautiful paper of Greg Muller about skeins and clusters. And I should also mention Bonahon-Wong had some really influential papers about the relationship between skeins and clusters. But that was really about skein algebras and certain cluster embeddings. And here you're really seeing the whole package. So it's more general than those works. So in this way, you can recover what are called the A, X, and P varieties of Gantraf and Gantraf-Shen. Now, at the moment, this is for the group G equals SL2, but we plan to extend it. I think that the topological picture is essentially the same, and as people who know who work in clusters will know that you need to then sort of the tori that you get and the mutations that you get are more complicated for general groups. So to pin down the topology, we started with G as SL2. Okay. Maybe before I go on to talking about higher dimensions, I'll see if Sheldon wants to relay any questions.
No, all questions have been answered in the chat.
Okay, fantastic. All right, so far I've been talking about surfaces, but I want to get on to three manifolds. But first I want to explain this remark at the beginning that I think skein theory, as I'm discussing it here, is fundamentally four-dimensional theory, and we should look at the Kapustin-Witten picture rather than the Chern-Simons theory, which is maybe more obvious if you're thinking about quantum topology. So as an algebraist, for me, the main reason for this is that braided tensor categories naturally form a four category. So this was constructed actually quite recently. It's been a folklore that it should be true, but it was rigorously done quite recently by Rune Haugseng in one set of axioms, and then Theo Johnson-Fried and Claudia Scheinbauer in a complementary set. So it's a four category. So the objects are braided tensor categories. The one morphisms are these central tensor categories, so these line defects between braided module categories. The two morphisms are bimodule categories, so a point inside a line inside the plane. That's the two morphisms. And then the three and the four morphisms are just the sort of stuff that you get because you're talking about categories, so the bimodules and the natural transformations. So that is naturally a four category. And if you're familiar with the cobordism hypothesis, then you know that if you have a four category, then you at least have a hope of defining a four-dimensional TFT. But you have to check a certain axiom called n-dualizability. And if you can check n-dualizability, then the cobordism hypothesis produces for you an n-dimensional TFT. In work of Kalak and Scheinbauer, it was shown that all braided tensor categories are two-dualizable. Of course, their work was more general. It was that all EN algebras are n-dualizable. So you get two-dimensional TFTs from any braided tensor category. Then in work with Adrian and with Noah Snyder, we showed that if your braided tensor category is rigid, and actually in a fairly weak sense, it's what's called CP rigid. But so if projective objects have duals, then in fact you get a three-dimensional TFT. And so we're studying rep QG, for instance, Q can be generic, it can be a root of unity, any of these theories are in that same paper, we showed sort of after Fried and Telemann and Walker, who had given many illuminating talks on this, that braided fusion categories are four-dualizable. So this is a common pattern. To get to n-1 dualizable, you need fairly reasonable restrictions, but to get to n-dualizable, the very top, you need a really strong restriction. And so indeed, braided fusion it's sort of too small to be interesting from the point of view of character varieties. You'll never get an interesting variety out of that sort of thing. And let me also mention with Adrian, with Noah Snyder again, and also with Pavel Safronov, we showed that modular tensor categories, whether or not they're semi-simple, are invertible. And so these give rise to invertible topological field theories, which is an interesting topic for many people. And so these invertible theories are sort of non-semi-simple analogs of Crane-Yetter theory. And so from these invertible theories, you can kind of extract the Witten-Reshetikhin triad invariants and the Chern-Simons theory. And roughly an invertible 4D theory is its corresponding 3D theory. It's not much more data than the corresponding 3D theory. But when you're non-invertible, there just isn't a corresponding theory that plays the role of the Chern-Simons in the same way that the Witten-Reshetikhin triad theory attaches to Crane-Yetter. Okay, so I really want to emphasize that even just from purely mathematical point of view, we think of this as a 4D theory. Okay. So I just want to close with some applications to skein theory and a conjecture. So recently with Sam Gunningham and Pavel Safronov, we proved a conjecture of Edward Witten, which is that if this quantum parameter Q is generic, and if we have an arbitrary closed and oriented three manifold, then the skein module of that three manifold is finite dimensional. So I think this is interesting because if Q is equal to 1, this is very false. By the result of Bullock, Froman, and Kanya-Bartoszyńska, when Q equals 1, this is the character variety of your three manifold. It's some interesting algebraic variety. It's basically never going to be finite outside of like lens spaces and Poincare sphere and a few examples. But nevertheless, the skein module is finite dimensional. And so that in particular, there's an integer valued invariant of three manifolds that we know exists, but there's very few computations done. And this integer valued invariant satisfies TFT axioms. Maybe I'll just say briefly that when Q, if we take the opposite extreme, when Q is a root of unity, then with Jordan Ganev and Pavel Safronov, we showed that the skein algebra is sort of azumaya, which means that it's relatively invertible over its center. So it's basically the same size as the classical thing, even regarded as a category. So I just want to talk briefly about the ideas that go into the proof of Witten's conjecture, because I think some of them might have more general applicability. So it's important that we lift, so you could have stated Witten's conjecture without mention of character stacks, but it was very important that we lift to the character stack so that we could have access to the skein category. And so what we do is if we choose a Heegard splitting of M, then we can, because it's a TFT, we can just write the invariant of the three manifold as a composition of those two things. So what we're able to do is express the category attached to a surface as a quantum Hamiltonian reduction of its puncturing, as I said before. And something which is very powerful is that we can write this composition, which even classically involves some sort of computation with stacks, just as a relative tensor product of this module tensor with this module over a certain algebra. And the algebra that we tensor over is really nice. It's exactly this AGS algebra, Alexeyev-Gross-Schomerus algebra. And the thing about that is we've lifted the problem first from the character variety up to the stack, and then off to the side over to the framed character variety. And we're showing that you could do the computations with the framed thing, so the gauge fixed story rather than the gauge quotiented story. And we show that you get the same answer when you work there. And so this is really powerful because at the framed level, everything is smooth and just almost trivial. So the framed varieties are just the handle bodies are just G raised to the genus number of copies, and the surface you're gluing over is just G raised to the 2G number of copies, and you're actually just intersecting these Lagrangians at the quantum level. And so then there's these beautiful results of Kashiwara-Shapira that tell you that you can, sorry, that should be Shapira, apologies, that tell you that you get finite dimensionality. So it appeals to the theory of holonomic D modules, for instance. Okay, so you relate it to some very classical and important theorems in geometric representation theory. Okay. So the fact that you could do this at the framed level, I think, is very interesting because we had this correspondence. You have the Fukaya category on the one hand, and you have these deformation quantization modules on the other hand. And we're saying that, well, the Fukaya category of a stack is sort of hard to define, but at least for this one computation, you don't have to, on the deformation quantization side, you don't have to worry about the stackiness. You can just do the framed computation. Okay, so I'm very aware of the time, so I'll just close with the conjecture that I wanted to explain. So right, So I hope that I've convinced you. I'm just recalling the basic facts here that Kapustin-Witten equations are very intimately related to these character stacks, and our expectation, I admit, even at the sort of physical or even hand wavy mathematical level of rigor, I don't have a super convincing proof that varying psi really is the same as varying q. But nevertheless, we expect that for generic values of q and the corresponding generic values of psi, this z of m that we're studying, the skein module of the three manifold, is the zeroth part of the Kapustin-Witten state space of the manifold. And so if this expectation holds, then the following conjecture follows, that the dimension of the skein module of an arbitrary three manifold at generic values of q will coincide for the group G and its Langlands dual. So this is a tantalizing conjecture because the skein module for the group G and the skein module for its Langlands dual group, they don't have at all a similar diagrammatics. If you do computations directly, you wouldn't necessarily see this. But nevertheless, so Sam Gunningham has done some computations on the three torus and for lens spaces for the groups SLN and PGLN. And at least there where we can do some computations, you get two formulas which have a different structure, but you can check by computer that they match and they match and they match. So I'll close there. Thank you.
Thank you, David. Please join me in thanking you. Let's start. Okay, so we're going on to questions and answers. So please raise your hand in the chat. There was some in the participants menu. I saw there were some unanswered questions in the chat. So those of you may want to raise your hand again. First question, Sergey Gukov. Let's see, let me go. Can you so let me unmute you here.
Thank you, Sheldon.
Go ahead.
Thank you, David, for a very nice talk. I really enjoyed it. I have a quick comment and a question. The comment is, in work with Putrov and Vafa from 2016, we studied state spaces, what you call Z of M in twisted n equals 4 4D theory on three manifolds. And we had a conjecture that, well, of course, based on physics analysis, so it was supported by physics, that it's a Grothendieck group of a tensor category. So in fact, the skein module should be categorifiable, but also it gave a practical way to compute S and T matrices. So another conjecture is that, which is probably a refinement of yours, is that Z of M carries representation of SL2Z. And we computed some S and T matrices in various examples and network and follow-up work. So would you not expect SL2Z action, and wouldn't be natural to have that? It would be nice actually to compare that representations.
Yeah, so, well, first of all, let me say that I know that there is work about categorification of skein modules, but just to differentiate, that's not a part of what we're doing here. So I don't have anything much to say about the very interesting work that's being done about categorification of skein modules. And I think seeing that from this point of view, it would be a bit distant. But about the full SL2Z action, I think that sounds reasonable. I mean, this is just the S-duality that's supposed to appear here. So yeah, I wouldn't be too surprised to see the full SL2Z action. Yeah.
Do you have any thoughts on how to compute matrix elements? For example, for lens spaces, Poincare sphere, and other Brieskorn spheres, we had some predictions.
Of the dimensions?
No, matrix elements of S and T matrices acting on Z of M.
Well, but so it's a bit different, right? We're saying that it's not that the skein module itself has an SL2Z action. So that sounds a bit different. I'm saying that the S-duality changes the gauge group as you would expect. So it's that the S matrix is, Langlands duality is between the skein module for G and an a priori completely different vector space, which is the skein module for G check. So there's no way to think of that as an SL2Z action on the skein module. It's something that changes your gauge group and therefore changes the vector space.
Well, there is an identification. I don't want to take too much time, so I'll probably make a comment and just leave you with last question or remark. But for SL2, for example, you can look at the congruence subgroup gamma 0, 2. So that would be acting perfectly fine on just one space. So it's a question of, and yeah, you can even try to look at full PSL2Z action on SU2, SO3. If you want, we can discuss it later. Again, I don't want to take too much time.
Sounds good. Thanks.
Hey, are there other questions? I don't see any hands, but Tudor had a question. I will have to manually unmute him. There you go.
I can unmute myself. I can unmute myself, but I don't seem to be able to raise my hand as
okay. Whatever works.
Yeah, thanks a lot, David. It was just about this thing you said very briefly about the lore that's now been proven that braided tensor categories form a 4 category. How does one like sort of think of that in some physical picture of 4D TFT? And my guess was that this is maybe just the empty 4D TFT with all possible 3D TFTs as their boundary conditions, but wanted to see if you had a picture for why this statement is true.
I can't exactly say that I have much intuition in the direction that you're talking about. I guess one thing I could remark is that sort of all the two-dimensional pictures that I was drawing at the outset, I think, you know, from a 4D Kapustin-Witten kind of point of view, I was really always thinking about some surface cross R2. And the sort of, the R2 is the algebraic direction that's encoded in the category structure, the fact that you have bimodule functors and natural transformations. And then the topology becomes clear. Then you can do some natural topological operations on the surface. But you know, yeah, I guess that would be the answer that I would want to give. Of course, then you need to worry about orientability of the theory, and that's also an interesting question. But I'm not sure I can really give a physical description. To me, it's fairly straightforward that you get a 4 category in this way.
Yeah, there should be some nice description. Yeah.
I mean, I think I want to say like surface operators in a 4D theory form a category, and so that's also true here, and that's the kind of structure that's arising. If you go down the sort of, if you go down in codimension, if you go up in codimension, you also go up the category ladder. So you have numbers at the top, and then vector spaces, and then categories, and then monoidal categories, and then braided monoidal categories. And so I think, yeah, so I think maybe a satisfying place to land with braided tensor categories is that they're sort of the local surface operators.
David, question. This is Nitu Kichlu.
Sure. Hi.
Hi. I was wondering, what assumptions are you making in the characteristic of the field if you're looking at categories? At what point do you have to make assumptions, or do you even have to make assumptions?
Oh, that's a good question. So you can talk in, so most of what I'm talking about in generality holds for perfect fields in finite characteristics. So for instance, this slide here, Haugseng and Johnson, Freud, Schambauer, I mean, they're working with like, you know, complete Siegel spaces and some generality that is way more general than that. For the existence of this, for these dualizability results, you have them, you just need to be a bit more careful. So for instance, the notion of braided fusion category, you should talk about separable tensor category. So you need to tie in the characteristic. But certainly you can make sense of everything that's been in the talk. For the I would have to think a bit about the for instance, the finite dimensionality result, because you know, we use this story with of Kashiwara Shapira, and that is really a story about sort of in the complex analytic topology, and you can just barely transfer it over to the algebraic world that we're working in. The way these things go, I would guess that maybe for like all but a finite number of primes that you could apply their machines, but I'm just guessing usually.
Right, and this might be relevant to Sergey's question of categorifying this whole thing, right? I mean, because in some question is a question about all of the understanding, right? There should be some sort of global construction that you're making in the background that's independent of characteristic. Or at least if his suggestion that there is a way to categorify the skein modules.
Well, I mean, so there are ways that people have studied. For instance, there's this Morrison, Walker, Vedrick, and some other recent papers about categorifying skein theories. Yeah, I think that a natural question for me that I don't know the answer is, what sort of structure do you expect from those theories? I mean, they won't be, there's somehow something like 5-dimensional theories in the sense that you categorified the 4-dimensional theory, but they certainly won't satisfy this kind of cutting and gluing formulas that we're discussing. So yeah, I mean, those categorifications exist, but I don't know exactly how I would fit them into this, how I would relate them to this framework.
Thank you. That's very helpful. Thanks.
We have a question from Greg Moore. Greg, could you unmute yourself, please?
Yes. At one point, I think you said that modular tensor categories are all invertible, and I found that a little surprising.
We did too.
You're certainly not saying that modular tensor categories, you know, the 3-dimensional topological field theory is defined by modular categories. Modular tensor categories are invertible.
No. What I'm saying is that
wouldn't be true. So,
no, that's
so
not what
in
I'm
what
saying.
sense are modular tensor categories invertible?
Right. So yeah, thank you for that question. So, so something that people have known for a long time is that I've known in a somewhat folkloric sense is that modular tensor categories define invertible 4-dimensional theories, not 3, but 4. So these are the Crane-Yetter theories. So Crane-Yetter, we're considering semi-simple modular tensor categories, where you can write down, for the 4 manifolds, you can write down an explicit sort of state sum description. And one of the first things they show is that the theory only depends on the Euler characteristic and one of the first characteristic classes I can't remember is the genus. Yeah, just the Euler. No, sorry, I forget the second one. Somebody probably has already answered in the chat, so look there.
Okay, that's what I was wondering. So you're really saying that the anomaly theory is invertible, associated to the 3D.
That's right, that's right. And so so I think from a physical point of view, in the semi-simple case, that is a well-known feature. But I think in the non-semi-simple case, it's not been very much considered as far as I know.
Okay, good point. You're not assuming anything like unitarity of the. Absolutely,
unitarity would rule out. Unitary would imply semi-simplicity. So there has been a lot of interesting work recently by Petro Morand and Blanchet, Nathan Gear, Gaidutinov, trying to directly construct non-semi-simple versions of Witten-Reshetikhin-Tarayev theory. So working with the 3D theory, And sort of the point of view I would like to advocate is that you have this invertible 4D theory, even without the assumption of semi-simplicity. So then you can try and view it as the anomaly of something, and that something should recover the non-semi-simple 3D theory.
Okay, thanks. That's clear.
Thank you.
So Sharyar Sikandar has been waiting to ask a question patiently. Can you please unmute yourself?
Yes, thank you so much. And thanks for the talk. I have two naive questions. The first one is about the action of the mapping class group on categories. And I'm just wondering if any of the Thurston theory can be derived from this action. So for example, does the action distinguish or can it figure out the Thurston classification that the mapping class is either finite order, reducible, or a pseudo-Anosov? And secondly, if it is pseudo-Anosov, can one read off the stretch factor of the pseudo-Anosov from this action on a category?
So let me go back to that slide. So that one's an easy one to answer because I don't know very much about this action. So you know that you have these mapping class group actions. I think it should be very interesting to study them. I should clarify that it's an action of the mapping class 2 group. So meaning that when you talk about mapping class group action, you typically are looking at diffeomorphisms of the surface modulo isotopies. So here we have diffeomorphisms, isotopies, and isotopies of those. And then we stop. So it doesn't go on forever, it goes up one more level. So this is called the mapping class 2 group. So the point is that you have an action by functors, but then those functors have themselves natural isomorphisms at inner end. I think it's a very interesting question to study these mapping class group actions. You can see them quite explicitly as they act on the Alexeyev-Grossa-Schomerus algebras because they just act through their action on pi1. But as far as the sorts of questions you're asking, I don't know what sort of power they have for distinguishing different classes of surfaces. Yeah.
I see, thank you. Just to mention, the guiding problem in low dimensional topology is to find a finite dimensional faithful linear representation of the mapping class group. So and then when you said it acts on this finite dimensional algebra that might be related to it.
Yeah, thank you. Actually, I did mean to mention that. Yeah, exactly. So if you take a surface across a circle, then you have a pretty good control. Those were the cases where, at least conjecturally, we have formulas for these dimensions. And for instance, it's a theorem of my head is Carrega and Gilmer showed that for the SL2, for the Kaufman bracket skein algebra, you get a 9-dimensional vector space. And so there's this 9-dimensional vector space as an action of SL2Z, and you can decompose it for SL2Z in that way. So yeah, I agree. It would be interesting to sort of study these families of representations. I mean, that's one way that this faithfulness of braid group actions occurred in one proof of this was using quantum topology. It's natural to wonder if you could do that here.
I see. Cool. Thanks. It's just that SL2Z is the mapping class group of genus 1, and the conjecture is for genus bigger than or equal to 3. Actually, even genus 2 is not.
Okay. Thank you. Yeah.
So I had another naive question. Do you know what is the de Rham or the Dolbeau version of these quantum character stacks, where you're looking at representations into quantum groups?
Yeah, so I sort of touched on this very briefly here. The de Rham or side, at least, is you're looking at the sort of traditional geometric Langlands as was proposed by Beilinson and Drenfeld. So
right.
You're looking at D modules on Bungie, and yeah.
But this is not the quantum version. This is what appears in the Beilinson Drenfeld
Right. So Behrens and Drenfeld did not they mentioned but did not study in great detail quantum, the quantum geometric Langlands duality, but that it does involve this parameter psi here.
Okay, okay, that's okay. Okay.
So you can study both cases. You're studying D modules on Bun-G, but with different parameters of psi related by an inversion. That's right.
I see. Cool. Thank you.
Thanks.
And so before we thank David again for a great talk, which generated lots of questions and lively discussions, I'd like to remind everyone of our schedule. Due to the US academic semester, we have gone back to meeting once every 2 weeks, except that last week was the US Labor Day holiday, so we skipped a week. And we are meeting again next week, and our speaker will be Lauren Williams, talking on how is the hypersimplex related to the amplitude-hedron. And now let's get back, and thanks David once again for a wonderful talk. And hope to see you next week.